So we're now at the stage where we're considering the implications of uncertainty. So I hope that the subtlety and surprise element of the class will gradually pick up without increasing the difficulty. The complexity will pick up a little bit, but not the difficulty. It's just you'll have to keep a few more things in your head, but the mathematics isn't any harder. So we ended last time talking about default and inferring default probabilities. And so I just want to finish off that discussion. So suppose that at any stage of the tree, lots of things can happen in the world. We're always going to model the uncertainty in the future by a tree with different things happening. And at each of these nodes, people are going to have a discount rate. So maybe it'll be, R equals 20%, and here R could equal 15%, something like that. And we want to add to this the possibility that there's default. So if we add the possibility of default, and these things keep going, and maybe there are payoffs at the end or payoffs along the way. If at any point in the tree like this one, we add a new possibility, which is the default possibility, and we assume, so this happens. By the way, when do people default? They never default before they have to make a payment. So when do they default? Exactly when they're supposed to make a payment. So suppose that this guy is going to default here when he's going to make a payment. At every possible scenario, he would default there. So we've got a very simple model of default. Okay, so not a very realistic one where the guy defaults in all of these following scenarios. Okay, so something's just bad. Once he's gotten here, you know that he's not going to make the payment the next period. And let's suppose we further assume that not only does he default there, but he defaults on everything thereafter. So the payoff is just going to be 0 here. So this is going to be, originally we had probabilities P1, P2, P3, let's say for the probabilities. Now we're going to have probabilities D for default, and then 1 minus D times all of these. Right? So essentially, what have we done? We've simply replaced, in our calculation of payoffs and present values, we've simply replaced these possibilities with probability P1, P2, P3. We added another possibility, but the payoffs are 0 here. Nothing's going to happen from then on except 0. And we said that happened with probability D, which means presumably all of these have to be scaled down by that, so they still add up to 1. So essentially, the point I'm trying to make is that default that leads to 0 payoffs thereafter is just like discounting more. Why is that? Because whatever calculation you did for the value here of what the bond could possibly be worth there it's all the same numbers as there were before, except we've multiplied it by 1 minus D. Okay, so it's the same thing. So instead of going 1 over 1 plus R times, future payoffs, that's no default value. Okay, now, so that times future payoffs. Now we've got default value under this special kind of default is going to be 1 minus D times 1 over 1 plus R times the same future payoffs. Okay, but I always could make I could rewrite 1 minus D as 1 over 1 plus S or something. And so then I really have just 1 over 1 plus R times 1 over 1 plus S. So that's just 1 over 1 plus R plus S plus RS. So that's going to equal 1 over 1 plus R plus S plus RS times future values. Okay, so the effect of this special kind of default. We just get 0 thereafter. You know, the guy decides after this payment, I'm not going to make any more payments. I'm defaulting from then on. That's the same thing when valuing the future payoffs. It's the same thing as instead of discounting by R, discounting by R plus S with a little bit R times S. You know, if R and S are small numbers, this is probably quite a small number. So default probabilities get mapped into spreads, they're called. Okay, the way to evaluate it is you just multiply by 1 minus d, which is the same thing as discounting by a higher number, and that higher number is almost the same. It's very close to R plus d, as a matter of fact, because 1 minus d is 1 over 1 plus s. If d is very small, s is going to be very close to d as well. Okay, so an so what's the implication of this? The implication of this, in a special case again, where we just have, you know, no uncertainty except we have default. So here there could be d1, 1 minus d1, and here there could be probability of default 2 and 1 minus d2, probability of default 3, 1 minus d3, and we've got interest rates R0, so this will be I0, IF1, IF2. Okay, so if you knew what the interest rate was going to be today, you knew what the interest rate was going to be tomorrow, you knew what the interest rate was going to be the day after tomorrow, there's no uncertainty about interest rates, they're perfectly anticipatable, but you know that there's a probability of default each time. So in stage 1, this guy might default before making his payment here, in which case you're just going to get 0. In stage 2, he might default instead of making his payment, won't pay the coupon, he'll just default, or in year 3, he might default. Okay, so what's the implication of what we just said? You can evaluate this bond, the payoffs of the bond, so let's say it pays a coupon, C, 100 plus C. All right, the way you would evaluate that without default is you would just take the value of the coupon, the present value would have been you would have done it recursively. You would have gotten, you know, P3 equals 100 plus C. Then you would have said P2. You would have gone in your computer. You would have said P2 is 1 over 1 plus IF2 times 100 plus C. Okay, and then P1 equals, so the value here is the 100 plus C discounted by that forward rate. Then P1 would have been C plus P2 divided by 1 plus IF1. So you take the value here times that. So this is in case there's no default. And P0 would have been C plus P1 over 1 plus IF0. Right? So that's how you would have done it by backward induction. But now that you know there's a chance that there's default, you have to not multiply by 1 plus IF2. You have to multiply all these things by the probability of defaults. You'd have to multiply this by, if we change colors, by 1 minus D. You'd have to multiply this by 1 minus D2, and you'd have to multiply this by 1 minus D1 times 1 minus D2, and this by 1 minus, this would be 1 minus D3. This is 1 minus D3 times D2, and this is 1 minus D1 times 1 minus D2 times 1 minus D3. Okay, so this value would be the old value you got here multiplied by 1 minus D3, multiplied by this 1 minus D3. This value is what you would have gotten here, but you've already scaled it down, so multiplied by 1 minus D2, and this is 1 minus D1. So what's the upshot? The upshot is, had you, and so then this is, okay, so that gives you the price with default. Okay, so, yep.
So P0 should be multiplied by all three, or isn't it that you're taking whatever you get in as P1 is given and just multiplying by?
Well, I could have done it two ways. I could have written, so what you're suggesting is a better way, would have been to say P2, the default bond, P2 is going to be 1 minus D3 times P3, okay, which is also equal to P3, because there's no default after here. The world just ends. Then P1 is equal to 1 minus D2 times P2, okay? But that P2, remember, is already 1 minus D3 times P3, okay? And then P0 is going to be 1 minus D1 times 1 minus D2 times P1, but that's equal to 1 minus D1 times 1 minus D2 times P1, which is 1 minus D3 times P3. Right? Sorry, if you go from here to here, the value here is 100 plus C. So if P3 is just 100 plus C, let's leave it as 100 plus C. That's if the guy actually pays. Okay, so the present value would just be, then you have to divide all this by 1 plus I2. Sorry, this is 1 plus IF2. Oh, making a mess of this. And this is, okay, so usually you'll go back from here to here by discounting by the interest rate. Okay, but now we're going to have to also multiply by the probability that you default to go back here. So we get a lower number. P2 is not just 100 plus C divided by 1 plus IF. That's the discounting. You also have to multiply by the probability of default. Then when you go back one period further, you have to discount again. Okay, so I should have divided this by 1 plus IF1. You have to discount it. And also you have to multiply by the probability of default. Okay, but the thing you're bringing backwards is P2, which is already taken into account the probability of default the next time. Okay, and then when you go back one step further, you have to do the whole thing, again, divided by 1 plus IF0.
You shouldn't have a 1 minus D2 in there as well. Shouldn't you just be discounting by 1 minus D1 0?
I have 1 minus, this is P1, not P2. So I have a,
You've already discounted by 1 minus D2.
no. Okay, so, but I'm switching the P's on you. I've got a P, okay? So when you have P, when we go from here, okay, the value here we just calculated was going to be P2, okay? So here, the value P1, taking into account default, is 1 minus D2 times P2, okay, which already takes into account the default next time, times P2 discounted by the interest rate here. So I've got the 1 minus D2 here. Now when I discount back to here, you're saying, how come the D2's showing up anymore? Because I'm just at D1. That's your question, right? Okay, so it doesn't show up. It's just P0 is 1 minus D1. Oh, you're asking this. You're right. 1 minus D1, you were right, times P1 divided by 1 plus IF0. That's right. But if I plug in for P1, P1 already had, that's where the D2 came from. So P1's got the D2 in it. So it's 1 minus D1 times 1 minus D2 times P2. And then P2 had a P3 in it. So I've got all the defaults in it. Are you with me now? So sorry about that. So you were right. I said it wrong. So, okay, so but this isn't the point. This was supposed to be obvious. I didn't even think about it. The next step is the thing that's not obvious, okay? So to discount, you just figure, here are the potential cash flows. You're discounting them by the interest rate. You also have to discount it again by the fact that the guy might not actually pay you. So that gives you a lower present value. P2, yellow P2 is less than the no default white P2. When you discount again, you're discounting the yellow P2 by the interest rate here and also the fact that the guy might not pay. So you have to multiply by 1 minus D2 and also the fact that he might not pay the forward rate. Okay, and you keep moving that backwards. Okay, so that was supposed to be obvious, even though I made it sound complicated. What's slightly subtler is just saying the same thing backwards, which is, suppose that saying the same thing backwards is, suppose I knew all these forward rates, suppose I knew the forward rate, suppose I had a bunch of bonds. Suppose I had American bonds, coupon bonds. Okay, and so the American coupon bonds are going to, they're going to pay, the 1 year pays a coupon C1 and has a face of 100 and has a price pi 1. The 2-year American bond has a coupon C2, a face of 100, and a price of pi 2. And let's say the 5-year has something C5, face of 100, and a price pi 5. Okay, now from that, we know that we can deduce, what all the forwards are. We did that in the first class. Okay, so now suppose at the same time we have Argentina, where there are, many Argentine sovereign bonds promise payments in dollars, by the way. They're trying to trade them internationally. So let's say Argentina, we also have the Argentina bonds, C hat 1, 100, pi hat 1, that's the 1 year, down to the 5-year, which is the Argentina C hat 5, 100, and P hat 5. Pi hat 5, its price. Now let's suppose that Argentina could default, whereas America can't. So it's quite likely that pi 1 will be less than the American pi 1, and pi 5 is going to be less than the American pi 5, because all these bonds might default. So if the coupons were the same, if C1 hat was the same as C1 and C5 hat was the same as C5, the fact that Argentina could default obviously would mean its bonds would trade less for the American ones. So the question is, can you figure out the default probabilities very quickly in Argentina without having to do a lot of complicated calculations? Well, one thing you could do, and the answer is yes. And why is that? Because you could take this data and you could say, so we could just erase this here, we could say, assuming no default, we could explain these prices by finding, just like we did in America, the Argentine forwards. Forwards, 1 plus I hat 0, 1 plus I hat forward 1, and 1 plus I hat forward 4. Okay, so these are the Argentine forwards. Now these forwards would be much bigger than the American forwards. Why is that? Because the prices in Argentina are so much lower. If you're assuming there's no default, contrary to fact, how could you explain all these very low prices? Well, you must think that in Argentina, they've got very high interest rates and very high forwards, so they're discounting more, and that's why they've got lower prices. And we know how to get those forwards, assuming there was no default. So the trick I'm merely pointing out now is that if we now go back and say, aha, Argentina doesn't have different forwards because anyone in Argentina, the bonds are denominated in dollars precisely so that people can be crossover investors. An American can put his money in Argentina, or an Argentine can put his money in America, so you can move your money to either place. So it must be that the forward rates can't be different. If you knew for sure you're going to get paid in Argentina, you'd have to have the same forward rates in America. So the reason these forward rates are higher is because there's a chance of default. So what is the chance of default? So I claim the chance of default is, and I was supposedly, you're supposed to realize this now. If I'd been clearer before, you would see where I'm going. The chance of default is incredibly simple to find out. So it's 1 minus d t equals what? Okay, but in terms of forwards is what? It's not pi. This pi, this isn't the zero price. This is the big price of the bonds. So it's not pi hat t over pi t. What is it, though? Okay, this is going to be a bigger number than that. And in fact, that ratio is the default probability. So this is assuming, remember, that if the Argentine bond defaults at this period, say, it's never going to pay anything after that. You're going to get zero payoff, and all the other bonds, Argentine bonds, will also default. I claim that this is going to be this is the easy way of getting the default probability. And so the differences in the forwards is just explained by the default probabilities. And so the extra Argentine interest, if this is a higher number than that, you know, this is approximately 1 minus d is approximately 1 over 1 plus d, which is, and so it's basically, you know, this is very close to that. Basically, if all the numbers I and d are small, then if t minus 1 is approximately if t minus 1, the American one, plus this default rate in Argentina. Okay, so I should probably have a hat because I'm referring to Argentina with the hat. Okay? All right, so why is that true? I just argued it. How could that possibly be true? Okay, so you see what I'm claiming? That you have now a very simple algorithm for finding out, inferring what Argentina default rates are. You can just, again, I'm making a special assumption that when Argentina defaults, you get nothing. That really isn't the case. There's some huge convention that happens, and all the countries get together they defaulted on. They've got some big meeting, and, you know, someone like Brady invents some idea, well, they'll owe less, and there'll be a writing down of principle, by the way. So whenever this happens, there is recovery, after a writing down of principle. Okay, so what all the countries do is they say, okay, we know you can't pay all that you owe us. We'll settle for half of it. We'll write down the principal, and we'll hold you to that half, or to a third of it. Okay, and so this is one of the things we curiously haven't done in America, where all these homeowners can't pay, and we don't write down their principal. We just throw them out of their houses. But anyway, let's say you write the principal down to 0 in that special case. You could easily infer from the price of the Argentine bonds what the default probabilities were, and by this formula. And so the question is, why is that true? Okay, we know how to calculate the forwards in America, given the American data. That was one of the first things we did in class. We said that every American company in the whole country, financial company, is doing that. Everybody has those forwards calculated. Okay, now, if you're given the Argentine data, which is, after all, just coupons and the prices of the bonds, you could find Argentine forwards, assuming there's no default. But that, of course, is, but there is default. So it must be that they have access to the American interest rates and forwards, but the Argentine bond might default. But you see what we did when we did this calculation? The difference between the backward induction in America from here to here was just discounting by the American forward. Okay? To go to Argentina, we had to discount by the American forward and multiply by 1 minus d, so discounting it again. So all I'm saying is that in the US, when we went backwards, we just discounted by this thing. In Argentina, when you go backwards, you have to discount by this thing. So those things have to be the same. Okay, so the Argentinian discount is like taking the Hope I haven't got the thing. See, the American forward is going to be less than the Argentine forwards. It's going to be like that. Okay, so that's it. There's nothing else to show except that whenever you're going backwards here, you're discounting. Remember, you're discounting by the interest rate times the probability that you're actually going to pay off. And so that's what it is in Argentina. Hang on. Hope I haven't inverted one of these. Yeah, exactly. So if you write 1 minus d times the American thing in the denominator, so as I said, to do the discounting in Argentina, at every step, going back from here to here, what did we do in Argentina? We simply took 1 minus d, that was the default rate, hat, in Argentina, and discounted it at the American forward. Okay, so that's what I did here. So if I take 1 minus d hat, this is, multiplied by 1. So I take 1 minus d hat, multiplied by 1 over this. Okay, I just get 1 over the Argentine discount. And that's how we calculated, that's how we went backwards with our recursion. Just taking the interest rate, the discount, 1 over 1 plus I, times 1 minus d, and that's how we discounted going backwards. And so therefore in Argentina, if you're forgetting that there's default and you're just thinking you have to discount at the right rate and you're getting this discounts, you're getting this number. But in reality, you should have been taking this divided by that. So therefore figuring out this and knowing that tells you what this has to be. So it's extremely simple to deduce what the market thinks Argentinian default probabilities are year by year if you make the added assumption that once they default completely. And if you think you're only going to get a little bit back, well, then the calculation won't change that much. Okay? Yeah.
Can we also do it by using the price of zero?
Yeah, so you could also do it by using the price of zeros. But to me, the best thing is the easiest thing is using the forwards. But you could also do it by zeros. Okay, so that's all I wanted to say. All right, so, and as I said, the one last thing to say is that if these numbers are all small, then 1 over 1 minus d or 1 minus d is approximately equal to 1 over 1 plus d. Okay, that's, if d is very small, those are practically the same things. And then, if you multiply 1 over 1 plus d by 1 over 1 plus I, it's almost 1 over 1 plus d plus I. So it's almost this thing. It's not quite true, literally true, but it's very close to say that the gap between Argentinian forwards and American forwards is just the default probability in Argentina. And that reason is why it's called a default spread. Okay, you just add some spread to the interest rate, and you've so you can guess by the spread what the probability of default is. If it's a 6% interest there and a 3% interest, if it's an 8% interest there and 3% interest here, somebody must think the probability of default is 5% there. That's it. Okay. So let's now move to a tree where you have to make decisions. So I'm going to now describe the method of backward induction, which occurs over and over and over again. And we've used it a couple times, but not in its subtlest form. So backward induction. Okay, now who first invented the idea of backward induction? Well, the first person who spelled it out formally was Zermelo, who's in 1910, I think, that's within a couple years, a famous mathematician, Franco Zermelo axioms, and he proved that that there is an optimal strategy, in chess by backward induction. Okay, so for example, let's take a game. So we always are on a tree, but now we're going to use a slightly extended definition of a tree. A tree is going to look like this. So it's a root, finite number of branches from every. I want to formally define a tree. You know what it sort of looks like, okay? And there's no reason why the number of branches has to be 2 or even has to be the same from every point. But the reason we're going to extend it is the node is going to describe by who moves. So let's say white is moving here and black is moving here. Okay, now let's say the outcomes are a win for white, a win for black, a draw, or a draw. Okay, so the question is, so it's a two-move chess game. White moves first, up or down. Then after white moves, black moves up or down. And then the game ends. And depending on where position you reach, either it's a win for white, a win for black, or a draw. So what should white do? Assuming that black is a smart player, what should she do? So clearly, so what did Zermelo do? He said not only there's an optimal strategy, but you know what the outcome should be with rational players. So Zermelo said if white goes up, okay, then black is clearly going to go down and win the game. So white ought to be thinking here, if I go up, the game, although it won't end for another period, it's already lost. So the value of the game is already 0. Okay, so this method of backward induction attaches the value. Here we have values at the end. Okay, and so to figure out what the right thing to do is, by backward induction, you can propagate the values backwards. If black makes the right choice here, you know, the payoff is black gets the negative of white. So the right choices here are black could get -1 or could get 0. So black clearly wants to get 0. So black could win the game by moving down. So black surely will move down. So I should think of the game as already lost here and pretend that I had a shorter tree with a final valuation of 0 at this node. Similarly, if white goes down, doesn't matter what black does, the game is going to be drawn. So white should think to himself, the game is already a draw if I go down. And now white has an easy choice. Do I want to move to a loss or do I want to move to a draw? So clearly white, so I could just pick a move for black here. Clearly white is going to go down, and therefore with correct play, the game is a draw. So by backward induction, you figure out the correct play. Now why is this surprising? Because chess has an incredibly big tree, not an infinite tree. You know, there are all these rules that keep it finite. If you reach the same position 3 times, it's considered a draw. If you make something like 50 moves in a row without a pawn moving, it's a draw. Whatever those rules are, I used to play chess quite a bit, I've even forgotten. But whatever those rules are, they're designed to make the game finite. So the tree is finite. And so it's impossible to see the whole tree. And how should you know what to do at the beginning? Well, you don't know what to do at the beginning until you know what black's going to do afterwards, until what could happen later in the tree. But if you were fast enough to put the whole thing on a computer, you could figure out what to do at the beginning, because your best move at the beginning depends on what you think black is going to do next, which depends on what he thinks you're going to do after that, which depends on what you think he'll do after that. But if the tree ends, you can always go backwards from the end to the beginning and figure out what to do at the very beginning. Okay, so this is a familiar argument to all of you, I think. It was a beautiful argument in chess in 1910, and then it was anticipated, I mean, in mathematics in 1910. The chess players, of course, all knew about it. So Steinitz, who was a world champion from when to when, something like 1870 or so to, or 1880, let's say, to, let's see, 1921 to 1894. I think he was world champion from then to there. Lasker became the champion then. So he wrote a bunch of books and stuff in which he said, you know, there's a backward induction value to chess, but since we can't figure that out, on general principles, you can tell by looking at the configuration of pieces what the right possible move is. And so you can have positional, you know, you can have positional values. So I'll do that. And then you can have the backward induction values. So for instance, a positional value might tell you that, you know, having doubled pawns is a bad thing, having control of the center is a good thing, and you add up all those pluses and minuses, and you get these positional values. And so he said your positional, you know, if you've got the right positional algorithm, right positional understanding, your positional sense of what to do, you only need to analyze one move deep. You can figure out what the best position is going to be and move that way. And if you really understand the game properly, that positional thinking, that strategic thinking, so it's called strategic thinking, is going to give you the same decision as the exhaustive analysis of all the possibilities, which is tactical thinking. Okay, so the two should amount to the same thing. Now, in fact, people can't do the full tactical thing, and also they don't have the full strategic understanding either. So they kind of mix strategy and tactics, and that's what makes the game interesting. So no one has ever written this, but I'm sure there's an interesting study to be made about what games are interesting, and they must be the kinds of games where you can mix. There's always a mixture of strategy and tactics. In game theory, as we describe it in economics, there's no such thing as strategy. All this is out. It's all just backward induction, which is what I'm teaching you. So the way computers play chess, incidentally, is, and the guy who invented this is Shannon. So he's a famous, a famous professor of information systems, so an engineering professor. So he said, well, you can't look at the whole tree, which is too long in chess. So what you should do, so all this extends way further. Maybe you can only look 2 moves deep. So what Shannon recommends is look as far as you can put in your computer, apply some positional thinking to evaluate these positions at the pseudo end of the tree. So it's really not a win for white. Let's just pretend white's so far ahead that we'll call it a win and a loss and a draw and a draw. That's just by looking at positional values. And then having assigned those terminal nodes values, now by backward induction, you can figure out what the value is here and exactly what the right first move to make is. And then after white's move, black will come here. Black can now look 2 moves deep. So black's going to look from here all the way down here. He's going to do his positional evaluator to these nodes and try and figure out what they're worth, and then do backward induction to figure out what his right move is. Anyway, that's basically the idea of all chess algorithms, and then they've gotten refined by saying, well, anyway, there are lots of refinements. So I used to be very interested in this. I don't think I'll talk more about it unless anyone wants to ask me something. So there's the origin of backward induction, Zermelo's proof, and it's obviously a big deal in chess, and the chess players all knew about it before Zermelo, but they didn't write anything down as formal as Zermelo. So how does this apply to everything we do in economics? Well, I want to give a series of examples culminating in market examples, but starting off a little far from life. So the first one I want to give is the red and the black. So these are just 2 games. This is the first one I invented 10 years ago, but I don't think they're, anyway, I think they aren't that original. I thought they were when I invented them. But anyway, so the red and the black, it works like this. There's a deck of cards, 52 cards, deck of 52 cards. And you can, someone offers you, so half of them are 26 red, right, and 26 black, which is all I care about the cards. And someone offers you a game, and they say, okay, the deck's upside down, they've been shuffled. You can turn over a card, and if it's black, I'll pay you $1. If it's red, you have to pay me $1. So I'm offering you this chance to play this game. And of course, you can quit whenever you want to. I can't keep forcing you to play, so anytime you want to, you can quit. So that's the game. Can stop whenever you want. Okay, and once you draw the card, you throw it away. And so all these examples are going to be examples of stopping games. And you'll see in economics that when you prepay on a mortgage or when you call a bond, you're stopping the thing. The contract's ending. Life is going on, but that contract is ending. So want to know when's the right time to take an action like that. So red and black is a simple game like that where you turn over a card. If it's black, you're in the black, you win $1. If it's red, you lose $1. And you can stop whenever you want. So you have an option. So I'll call this an option. And most people totally underestimate the value of options. So let's just figure out how to figure out the optimal thing to do. What would you do in this game? Would you play if I gave you the chance to play? I think we did this on the very first day. Yes, you're about to say something? Your hand twitched. I thought, yeah.
I was going to say, yeah, we have decreasing marginal utility as well. So assuming we have a chance of drawing either, you wouldn't play the game because you would derive less utility from winning $1 than you would from in magnitude than the loss of utility you would get from losing $1.
Okay. So I'm going to now disagree with what you said, but it was very interesting what he said. He said, look, if you draw a card at the beginning, it's 50-50 whether you're going to win or not. If you win, you get $1. If you lose $1. 50-50 chance. You know, if you're a little bit afraid if a dollar loss is more important to you than a dollar gain, that's a bad, you know, that's right away, it's not very good. Not very good odds. I mean, it's barely even, okay? And if you're a little bit risk averse and it's barely even, you shouldn't play, okay? But now, is it really barely even, this game? Yep.
Well, I mean, I think you should play because even if you get the first 26 red, you might, at that point just go to the end and you haven't lost anything except like the time you spent playing the game. So, like, you might as well play on the off chance that you'll get some black ones first.
Right. So you can't possibly lose if you play this right. You can always go to the very end of the deck. We're ignoring, you know, good point. We're ignoring your utility of time. So you can always go to the end of the deck and assure yourself of 0. So this is actually a pretty valuable option to be able to stop. Like he says, you can stop. If the first one's black, you could stop, and then you've won $1. If a whole bunch of them are red and you lose, well, you can always go to the end of the deck and get 0. So you're never going to lose, and you have a chance of winning. So obviously you should play, even if you are risk averse. You should play. But now the question is, can we tell exactly? Suppose you're risk neutral. How many dollars do you expect to win? Would you guess? Yep. You'd expect to get 0. Okay? Now, he just made an argument that you should expect more than 0. Because, for instance, he said, take this strategy. Pick a card. If it's black, you win $1, quit. You're $1 ahead. So with 50% of the time, you're plus $1. If it's red the first time, just close your eyes and play to the end of the game, and you're going to get 0, because you're going to win 26 times and lose 26 times. So that's equal to 0.5. So there's one strategy that gets you 50 cents on average. You can't lose, and half the time you'll get $1. But that may not be the best strategy. Yep.
You play a bunch of times, and at worst you'll break even, and at best you could make, I guess, $26 if you hit all 26 platforms.
Right. Okay. So he's saying that, you know, this isn't ambitious enough. This surely gets half $1, but you could do much better. Like, let's just wait. You know, the first time, suppose you get $1. Suppose you get black the first time. So that gives you $1. Now, the trouble is the deck is starting to turn against you. Now it's 25 blacks and 26 reds. So what would you do then?
Stop, sort of.
You'd stop or keep going? Well, the deck is against you. So now your very next draw is unfavorable. And by the way, playing to the end of the deck is going to lose you $1 because they're 25 black and 26 red. So this argument that if you just play to the end of the deck, you'll break even, it's not true after you've already taken a black one out. So you could lose it. You know, from then on, you're starting to run a little bit of a risk. So we're ignoring risk aversion. We're just caring about expected dollars. The fact is the deck is against you. So should you play or not? And so first reaction is, hell no, the deck's against me. Why should I draw another card? But you still have the option of going to the end of the deck. So the most you could lose is $1 if you went all the way to the end of the deck. And who knows, maybe you'll get a run of more black cards in the beginning and make a lot more than $1. Okay, so you should choose another card. Okay, in which case if you get black again, if you got red on the next card, you'd be breaking even. But now it's 25-25, and by the previous argument, it's obvious you should pick another one, because the worst you can do is break even from then. But what if you got 2 blacks in a row? Well, now the deck is way against you. It's 26 red and 24 black. So you're, you know, now you've only got a 48% chance of drawing a black one the next time. The deck is going further against you. Should you really draw another black card? It seems, another card, it's, you know, it's more likely to be red. Well, the answer is yes. And suppose you got a black one again, meaning you're 3 up, and now the deck is 26-23. Sorry, I went the other way. 26 red, 23 black. It's getting further and further against you. Should you draw another card? Well, what you've got is you've got a bad deck working against you, but you've got this option working in favor of you. So the question is just how valuable is the option? And like I said, people always underestimate the value of options. And so, okay, go ahead.
When you want to play until your lose option, until your lose condition is either balanced out or worse than your win condition?
Yes, but what is that condition?
13 blacks.
You would take, if you got 10 blacks in a row, you would keep drawing blacks? Is that what you're saying?
Well, I mean, at that point, if you assume that that's all sunk cost, assuming that you pick another red and then play it at the end of the game, you could lose, what would it be?
13 more. So you're saying you want to keep drawing blacks until, if you played to the end of the deck, you would lose as much as you'd won up until that point. So you want to never run the risk of losing money, of losing more. Okay, but you see, that strategy would get you to quit after the first one. After the first black, if you ran to the end of the, your strategy doesn't make sense. You're always going to, by going to the end of the deck, you're always going to undo everything you've won until that point. Because you'll be zero no matter what if you go to the end of the deck. Yep.
Shouldn't you quit whenever you have $1? Because, say, if you have more black cards than red cards,
Yeah.
then the number of black cards left in the
Deck is less.
smaller than the number of red cards left in the deck. So
Yes.
you quit whenever you have $1.
No. So he's saying just the commonsensical thing. After you draw one black card, he would quit because now the deck is against you. It's 25 red and only 25 black. The deck's against you. Why go on and play against an unfavorable deck? You've got your dollar. Be satisfied and quit. That's his recommendation. But that's wrong, and it's because you're doing what everybody does. You underestimate the option. The option is incredibly valuable here, and now I just want to show how to compute what your optimal strategy is, and I think you'll be surprised, okay? You should keep drawing, not 3 times. If you got a 4th black card, okay, so you've already made $4. It's a sunk cost. You've got this horrible deck. It's 26-22. Should you keep playing? Yes, you should. Yes, you can. If you got if you get a 5th black card in a row, you're up $5. The deck is horribly against you. Should you keep playing? Yes, you should. So anyway, it's really shocking, I think. Okay, so now let's just see how to compute this out so that we don't have to argue about it. It's just a little bit of mathematics, and you just see how surprising this calculation is. So how would you do it? Okay, well, the key is to figure out how to put it into a tree. So I'm not going to draw the picture because it gets too complicated. But basically, what you want to know is how valuable, remember the tree in backward induction. It was take the thing at the end and then figure out by propagating the values backwards. So if I have black and red here, and I've got 1 black card and no red cards, the value to me of that is what? I'm going to win $1 for sure. If there's only 1 black card left in the deck and no red cards, I know I'm going to play to the end and get $1. And obviously the value of 2 black cards and no red cards is $2, etc. And I also know what's the value to me of no black cards and 1. If I know that there are no black, you know at every stage what's left in the deck because you've seen what came out before. So if you're at the very end of the deck with no black cards and 1 red card, what's the value of that position to you? 0. Not -1, 0. Why is that? Because you're going to quit. You're not going to play. The value, and that's the critical step. Seeing that this is 0, okay, someone said -1. That difference between 0 and -1, that's the whole heart of the thing. So 0 and 2, the value of that is also 0. You're just going to quit. Okay? So what in general is the value? What is the value of V if there are B black cards and R red cards? What's the value to you? Well, the crucial step is that you can choose to quit by not playing. So this is the value from then on to you. B, so B black cards left, R red cards left. You could get 0 by quitting. Okay, or you could draw a card. Now, what happens to you if you draw a card? What happens to you if you draw a card? Well, with probability B over B plus R, you win $1, right? But then you move on to the new deck. And so what do I write? V here. V of B minus 1 and R. Okay? But with probability R over B plus R, you drew a red card. So it's minus 1. But then you move on to a deck that has one less red card. And that's it. You either decide to stop, or if you've decided to draw a card, you know what the chances of getting a black card are. You look at the black cards, 26 out of, if I'm down there, it's 21 out of 47. Sounds horrible. 21 out of 47, I win $1. 26 out of 47, I lose $1. So the immediate draw is terrible. But if I get a black card, I move to this situation. And if I get a red card, I move to this situation. Okay, so that's clearly, okay, so do you agree with me that that's what the value is going to be? And so if you look at, okay, so now, okay, are there any questions? This is a critical formula, a critical spot. Does everyone, Sophia, you're now in trouble. Somebody came and said hello to me after class, and now I know a name. So does this formula make sense? Kathleen, yes? Is it Catherine or Kathleen? Catherine, okay. Catherine, so you agree with this formula, right? Okay, but this formula is the key. It's just like our tree. Once you know what the values are down here, you can always go backwards and figure out the value here. Okay, so so what is the tree? The tree is going to have, well, I'm going to draw it on I'll do it on a computer. So now we can just do this on a computer. I hope I don't have to do that. Okay, so you have this, by the way, in your, it's on the web. Oh, no. Why are all these, oh, okay, there aren't question marks. Okay, so here it is. So you can see that on this, I can do it with this, on this thing, it's, by the way, this was I did my own spreadsheet, and an undergraduate last year thought it was so messy that she just redid it for me. So this is her doing. It looks much better than I did. So anyway, here are the number of cards. This is what the number of black cards left. This is the number of red cards left. And then when you go to the, the corresponding coordinate like this one, this is the value of the game when you have one black card and one red card. It's even though there's an even deck, it's a favorable game to you. Why is that? Because you draw the first card. If it's black, which happens with probability 50%, you win $1, so you've got half $1. If it's red, which happens with 50% probability, you draw the next one, and so you end up with 0. And by the way, if you got a black the first time, obviously you stop. So you get 50% chance of $1 and stopping, or 50% chance of going to the end and getting nothing, so it's value 50%. But that's a bad way of calculating that number. She's got a much better way of calculating it. Okay, so what she said is if this is the, if you had, no red cards and only black cards, the value is to go to the end of the deck and just win them all. Okay, so if you've got only red cards in the deck and the top line is no black cards, obviously you should quit right away. So we've got this first thing trivially done. Now, how do you figure out this thing? Well, if you look at the formula up there, it's just the formula you wrote. Okay, we wrote, which is you could quit if you wanted to. So you have to take the max of 0. But if you go on and draw, I can't read what's written there. If you go on and draw, there's going to be, the probability of red. Okay, this is the probability of getting a red over the total number of cards times losing $1. Okay, plus what happens is you then move. If you drew red, then you go to what did she do? C4, where, oh, C4 is here. Okay, right. So sorry, I was getting confused with the card. So C4 is this squared. Okay, that's the value in here. So C4 says if you draw a red card the first time, it happens with this probability, the number of reds over the total number of cards. You lose $1, and then you move to the position C4, which is one back here, the one where you've got one less red card and just a black card left. Okay, on the other hand, you could have drawn the first time, not the red one, but the black one, okay, divided by the total number of cards, and you would have won $1, but then you would have moved to the position where you had one less black card, which is D3, which is up here. Okay, so instead of doing the whole game, she says, half the time you win, but then you move over to here and get that value. Half the time you lose, and then you lose $1, and then you move over to here. So she's done that. That same formula appears in every box. So all you had to do was just copy it. You know, it's max of 0, and then the chance that you're going to lose $1, which is the number here of reds over the totals, times minus $1, and then moving over to here. Or you could get the probability of winning $1 with the black cards, and then but then you would end up, so you win $1, and then you move up to here. Okay, so it's very simple. Now, so she's done it. And notice that although the deck is even at one card each, so it sounds like a fair game, it's not. It's a favorable game because you have an option. So you all understood that. But the thing is, the option is much more valuable than you think. So let's see what the value of the game is. Okay, it's when you had 26 black cards and 26 red cards. So we have to go way over to here. Sorry. Where am I going? It's not the right answer. Okay, here it is, 26.26. The value of the game is $2.6, not just half $1. You wanted to quit, wherever you are, at half $1. It's not looking up anymore. So you want, so you wanted to quit with a after the first draw, okay? But it's much better than that. So now, what the shocking thing though is, so this means with 26.26 you have a favorable game and you should draw. If you didn't draw, it'd be worth 0. So obviously you're supposed to draw here. If you get a black card, you're going to go here. So here you're down. You've gotten a card and you've got one more. It wasn't that likely you were going to get black, but if you did, 50% chance you go here. So you win $1, and now you're at this position. Now, if you were supposed to stop, you would have, if you were supposed to stop at that point, what would you have done? If you were supposed to stop at that point, you would have had value 0. So the fact that that number is positive is telling you, even when the deck is against you, 25, you can't see it, it's 25 blacks and still 26 reds, it's still a favorable game. You should draw a card. And if by some miracle you won $1, you would have moved to here. So now you're 26 red and 24 black, but the game is still favorable. You should draw another card. Okay, and if you win again, you're here. Now you've gone 1, 2, 3 times you've drawn blacks. You should still draw another one. 4 times getting blacks. You should still draw another one. 5 consecutive black draws. The deck is now 26 against you and 21 in your favor. You should draw again. The game is still slightly favorable. And it just seems shocking that could be the case. But this is the proof that it's the case. So anyway, that illustrates the power of the option of being able to continue. And if you work, you're going to work out low numbers 2 and 3 in the homework, and then you'll see very clearly why it is that this option is just so powerful. It's uncannily strong. So are there any questions about this? Yes.
I'm still a little bit confused. I know that the option value is positive.
Yes.
But the probability actually is a little bit against you.
Yes.
So especially when you, after 5 wins,
yes.
Why do you want another draw? Because yes, the option value is a little bit positive, but the probability is still against you. So, yeah.
This isn't the option value. This is the value of playing. Okay, so it says the option value is bigger than more important than the fact that the cards are against you. So he's asking, my TA is asking, how could it possibly be that the deck is now 26 red and 21 black, totally against you, and according to this calculation, you should still draw? He can't see the advantage in drawing, because the odds are pretty high you're going to get a red card next time. Okay? Well, that's true. You're going to get a red card next time. But the thing is, your downside is limited. You can never, here's a way of thinking about it, you can never, you're up 5 cards, you can never lose more than $5 from that point on, because you can always play to the end of the deck, right? Which means you lose the 5 back that you already won. So there's a downside. The downside of losing is limited here. On the other hand, there's a big upside to you. You might, by some miracle, draw 10 consecutive black ones at that point, and then you could quit. Okay? And then you'd have a big, so your upside is much bigger than your downside. Now, the upside's less probable than the downside, so it's not so obvious which is going to be bigger. Is the option value more important, or is the fact that the deck is against you more important? It would be impossible to intuit the answer, but we don't have to intuit it. We just proved it. We solved for the optimal strategy. Are there any other questions? It's quite amazing, right? This. I'm going to pause for a second. Yes?
How do you calculate the profit at a given position?
Okay, that's what we just did. So let's try it again.
I mean, like the total profit.
Okay, so what we did, this number V is the expected profit you're going to make if you start with B black cards and R red cards. And now the intuitive mind figures that if B is less than R, you've got an unfavorable deck and you should just quit. Okay? But that's not the case. You can figure out what the profit is. How? By doing backward induction. You couldn't tell what the value of this bond is here with all these defaults and stuff until you started computing backwards till you got to here. So the same way here. We know at the edges, it's very obvious when all the cards are black or all the cards are red, that's up here, it's obvious what the value is. But if you have a position here, you can figure out what the value is of being in that position of 1 and 1. You could quit and be 0, or you could say, what are my chances of getting a black card and winning $1? If I get a black card, then I move to this position. But I already figured out this position's value because I'm doing backward induction, right? That's got one less, sorry, if I draw a black card, I go this way. It's got one less black card. And we already know that value of that position is 0. So to figure out the value of this position, I know the chance of getting a black card. Then I'm going to end up in that position, which has value 0. Okay, I won't draw anymore. Or I'm going to get a red card, and then I'm going to move to this position over here, whose value I've already computed. Okay, so that gives me the value here. How do I figure out the value here? Well, it's now 2 reds and 1 black. So this looks really bad. Actually, this position, the value of this I happen to know, is 0. Okay, how could it be with 2 red cards and only 1 black card, actually the value of the position is 0? Well, what do? The chances of getting a black card the first time are a third. So V of 1, 2 is going to be a third, okay, of getting a black card, plus then I go to here, which is no black cards left and just red cards, okay, which obviously is 0, plus 2/3. Okay, 2/3 of the time I get a red card and lose $1, but then I'm going to move to here with 1 red card where I have V of 1 and 1, which I've already figured out the answer to, right? This was V of 1 and 1 has value 1/2. Okay, so therefore V of 1 and 2 is going to be 2/3 times minus 1 plus V of 1, 2, right? I just drew a black card, so it's no longer... No, I drew a red card, so it's 1 and 1. So I started with 1 black and 2 reds. A third of the time I get a black card. 2/3 of the times I get a red card. But after getting the red card, the position is now 1 black and 1 red. The red card disappeared. That's over here. Okay, so if I get a black card, I move to here. We know what if I get a red card, I move to there. But V of 1, 1 is worth 1/2. So that's equal to 1/3 times 1 plus 0 plus 2/3 times minus 1 plus 1/2, okay, which equals 1/3 minus 1/3, which equals 0. Okay, so starting at this point, you've got 1 red card and 2 black cards. It looks horrible to pick a card. 2/3 of the time, you're going to get the wrong card. But you still have a position that's actually equal in value. Because if you get that black card which wins, you stop. If you get a red card, you're now in a position that's equal deck, and the deck is that's favorable for you, because if you get another black card, you stop, and if you get a red card, you keep playing to the end. Okay, so Okay, so that's it. So how can you do this by backward induction? You have the stuff on the edges, and then you solve for all these things along the side here. And having done that, now I can solve for this one, because I've got up and to the left, and I do that whole row. Then I can do this whole row, and then I can just, by backward induction, do the the whole thing. And the computer does that instantly. So it figures out the value of every single node, and it's shocking what the answer is. So are there any other questions about this? Ben, do you? So.
I figured it out. Actually, initially, I'm thinking about it, and well, I imagine this value is actually an option value. For example, you could choose to play this game, and after you win or you lose, then you get an option that continues the game. And so I separate the option value to this.
Well, that is your option. The option is always to keep playing or to stop. Okay, so let's just do, but the value I wrote down is the value of the game to you, of being able to play the whole game however you want. Okay, so now let's do another example. Yes.
Would you call someone irrational who doesn't continue to play the game up to that point that you showed with the .05 expected payout?
Right. So if you got.
My question is it preference to risk, or is it actually like a rationality?
Right. So this is going to become very important very shortly. So his question is, I just proved, if you can call that a proof by computer, the computer proved that even if you got 5 blacks in a row, you should still draw another card. Of course, things are quite risky now because, there's a very good chance you're going to lose on that very next card. So he's saying if you're risk averse, maybe you would stop there. And how can you distinguish somebody who's risk averse from someone who's just dumb and can't make the calculation? So so that's going to be a question we're going to take up in the very next class. But I would say that it's usually because people are dumb and can't make the calculation. So they just don't realize how valuable, how favorable the situation is they're in by having this option to be able to play to the end of it, to stop when they want to stop. Okay, so let's just do one more example. Suppose that you are undergraduates and you want to get married. You've been told that's a good idea, and it's going to be a very sexist thing, but anyway, it's also a game I invented, which turned out not to be as original as I thought. So I call this the optimal marriage problem. So let's say you knew you were going to meet 1,000 women. You're telling it from the guy's point of view. You're going to meet 1,000 women. Okay, 1,000 women. And each woman you meet, her suitability, you can't tell until you meet her and talk to her. And after you meet her, each woman's suitability, is uniformly distributed on 0, 1. Okay, so what do I mean by that? I mean, you meet her, you talk to her, you get to know her, and then you just draw, and so before you met her, you have no idea how suitable she's going to be. After you've talked to her, you understand how suitable. The best is it's 1, the worst is 0, and it could be a draw anywhere between 0 and 1. Before you meet her, you have no idea. After you meet her, you know exactly how suitable she is. And there are going to be 1,000 of them that you're going to meet. You could meet. The problem is that after you've talked to a woman, you can marry her then, or if you move on, or you can move on, but once you've moved on, you can never go back to her. So the question is, so you understand the problem. The problem is that let's say the first woman is 0.95 or 0.90. You think, gosh, how suitable. This is a great match. But I've got 999 more women to go. Maybe I'll do better. And then you get zeros from then on. And so you've missed your 0.90. And so you're going to end up marrying the last one, who's maybe a 0 for you. That doesn't mean she's a 0, just for you a 0. So I'm trying. Anyway, so okay, so what should your optimal strategy be? And are you playing the optimal strategy? So what do you think just intuitively, what's the optimal strategy? Of course, we're going to do it by backward induction. But what do you think it's going to look like, the optimal strategy? Yes? Right. That is the actual, that's what's going to happen. We're going to prove this, but he's exactly picked. He said, you set a threshold here at the beginning. You'll marry her if she's above some number. You keep to that threshold for a while. Then you haven't married anyone. You say, oh, my God, I'm running out of women. And then your standards just collapse. Okay, so desperation sets in. Okay, so that's absolutely right. But the only interesting thing is to figure out how high the standard should be. So how high do you think it is at the beginning? What would you say the number is at the beginning? Okay, now let me give you a hint. If you divide up, okay, so here's 1, and there's 1,000 women, so here's 0. Okay, so they're randomly picked. So if you could look at all the women and pick out the most suitable one, what would her suitability be? Well, her suitability would be, so the top on average will be something like 1,000 over 1,001. Okay, this is a famous problem. If you take n people randomly, you take n numbers, you pick randomly uniformly in 0, 1, the top one on average is going to be, if there's 1,000 women, it's 1,000 over 1,001. Second top is going to be 999 over 1,001. So this very standard statistical result actually was derived by a former Yale professor in World War II. The Americans captured German tanks, which had all their serial numbers on them. And the first tank was number 1, the second tank was number 2, the third tank they made was number 3. So we captured a bunch of them, and then we had to guess how many tanks did they make. Anyhow, so it's related to this idea that if they're uniformly distributed on 0, 1, the top one's going to be on average 1,000 over 1,001, 999 over 1,001, etc. But now you've seen, so what standard would you set for the first one? Right? You have to set some threshold here. Here's 1, and here's 0. By the end, you'll take any, but the last woman you're going to take her no matter what. So what should the threshold be? Well, it's hard to tell. We can't do it except by backward induction. So what would you guess? 1, well, then you'll never take her if it's 1, because the odds of getting exactly 1 are 0. So what would you guess? So you'd set the threshold this high, 1,000 over 1,001. Okay, so that means you're expecting to get as good a woman as if you could go to the very end and look at all of them. You never make a mistake. I told you there's a chance you'll make a mistake. The first one's the best. It doesn't quite come to your threshold, and all the rest are worse. Then you end up with a disaster here. So you have a chance of not doing that well. So you're setting too high a standard here, because you have a very good chance of saying no to all these women and then ending up with what's right. Okay. However, you're on the right track. So amazingly, this is the answer. This is the threshold. Okay, so you should set the threshold at where you expect the second highest woman to be, second highest match to be, and that is why there's so many novels about the other woman. Because if you're playing optimally, you should be ending up with the second best woman, and there should be one other woman that at the end of your life you regret that you didn't wait for, but only one other woman. So anyway, I just want to prove this to you in the same way we proved it before, just by solving for backward induction for the optimal. So we can just do this by backward induction. We know exactly what to do, okay? So it's one thing to say what you should do. It's another thing to prove that's what you should do, and I'm going to prove it now. So you can just see by backward induction how easy it is to do these things. Okay, so it's only, I'm going to have to take 4 minutes. If you can hang out for 4 minutes, we'll get this. So what happens with 2 women left? What's V of 2? What should you do? What should your threshold be for 2? What should your threshold be for 2 women? So here's the threshold. And here, V of 2, and okay, so I'll tell you. Threshold for 1 threshold for one woman is 0. If it's the last woman there, you know, whatever she is, she's, you know, that's it. You're going to might as well marry her. It's only going to can't be negative, okay? And then the value, unlike Herodotus, the value of 1 is going to be a half, right? Because if there's one woman left, you're going to take her no matter what, and on average you'll get a half. So the question is now, what's the threshold when there are 2 women left? And what's your expected payoff? So what's the threshold if there are 2 women left? You see the second to last woman, you talk to her, you find out how good the match is. You should take her if she's above, the match is above what? No, there's only 1 woman left after her, so a half, right? Because if you don't take her, you're going to go to the last woman. On average, you're going to get a half. So there's no point in taking someone whose match is less than a half when the very next step, on average, you're going to get a half. So your threshold is a half. So what's your expected quality of the match? Well, with probability a half, with probability a half, she's going to be above a half. And if she's above a half, she's going to be halfway between 1 and a half. So it's 3/4. And with probability, with probability a half, she's going to be below a half, and you're going to pass on her and go to the last one, and it'll be on average a half. Okay, so this is 3/8 plus, probability a half, she's going to be 3/4, and probability a half, she'll be a half. So it's 3/8 plus 1/4 is 5/8. Okay, now what if there are 3 women? What should the threshold be for 3 women, and what's the value of 3? Okay, so the threshold should be V of 2, which is 5/8. Okay, and what's the value? The value is going to be, what's the chance that you take the one you just meet? Well, the odds that she's above a half is 3/8. So it's 3/8 times the average of 1 and, you know, halfway between. So she's above 5/8, so she's somewhere between 1 and 5/8. So that's going to be 1 plus 5/8 over 2, okay, plus 5/8 of the time. You pass on her, and then you get 5/8. So that equals, if we just do that in a little bit more generally, it's 1 minus V2, okay? So that's 1 minus V2 times 1 plus V2 divided by 2 plus V of 2 times V of 2. Okay, so that's what that's the formula. So in general, V of t, okay, you set the threshold at V of t minus 1. So with probability V of t minus 1, you're going to get 1 plus V of t minus 1 divided by 2, and with probability 1 minus no, this is 1 minus V of t minus 1. With probability V of t minus 1, you're going to pass on her and go to the next thing, so you get just V of t minus 1. Okay, so that's just a formula. V of t equals some function of V of t minus 1. So you can program that into a computer, which is, so I'm ending now with this one picture. That's the end of it. Sorry, I know I've gone over, but this is the last picture. It'll only take a second. So 0 yield curve optimal marriage. Okay, so here it is. Here's, with one woman, your value, oh shit, sorry. With one woman, the value is a half, 1 match to go. Okay, so the number on the left is, with 1 match to go, the value is a half. With 2, it's 5/8. With 3, we computed that too. So you can tell for however many women you want. Now what I've done on the right number is this n plus 1 over, it's n over n plus, n minus 1 over n plus 1. Okay, so that's the second best woman, how good she'd be on average for you. And as you go down further and further, you see these numbers are getting to be the same. So this number and this number is practically the same. And if you go down to the very bottom, you'll see they're identical. Okay, up to an incredible number of decimal places, you get these two numbers are the same. So if there are enough women, you're going to get exactly the second best, and it's going to be the problem of the other woman. But anyway, the point of all this was to just illustrate how powerful the option is. It's as if you could go to the very end and pick out the second best one, even though you have to do them sequentially.